We have here more tests to determine whether or not a series converges or diverges. Here we consider the ratio and the root test. First, the ratio test. The ratio test is a very straightforward test, very similar to the limit comparison test. But here we only deal with the given series. So let the summation of a sub n be a series with non-zero terms. The series is said to be convergent absolutely when the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1. We get divergence when this limit is greater than 1 or obviously infinity. The ratio test is inconclusive if the limit of this ratio is equal to 1. So with that in mind, let's consider the first problem by making use of the so-called ratio test. So here we take the limit as n goes to infinity of the absolute value of 1 over 5n plus 1 divided by 1 over 5 to the nth power. This is the limit as n goes to infinity of the absolute value. This becomes 5 to the n divided by 5 to the n. Here, this 5 to the n plus 1 is 5 to the n times 5. So obviously the 5 to the n's cancel out. That doesn't make sense why I have to even do that. But anyway, this is the limit as n goes to infinity. You could drop the absolute value sign. The terms we're dealing with are positive anyway. We get 1 over 5. This limit of a constant is 1 over 5. It's less than 1. So by the ratio test, this series converges. Well, what about this one? The limit as n goes to infinity of the absolute value of, take the ratio, the n plus 1 ratio divided by the nth term. This is n plus 1 factorial over 3 to the n plus 1. And that's divided by the original sequence, n factorial divided by 3 to the n. So this is the limit as n goes to infinity. Notice that all these terms are positive, so you can lose the absolute value here. If it's alternating series, the absolute value just wipes that out. And sometimes they leave it, it's fine. I'm going to just leave it for now. The numerator here is n plus 1 times n factorial, and this is times 3 to the n downstairs. It comes up here, times 3 to the n. And this is all over 3 to the n times 3. This is 3 to the n plus 1. And then that's times the n factorial. Now the n factorials cancel, and the 3 to the n's cancel. So that has us left with the limit as n goes to infinity, and this is n plus 1 over 3 this goes to infinity. And so by the ratio test, if the limit is either greater than 1 or infinity, then the given series diverges. Consider this one, the limit as n goes to infinity of the absolute value of n plus 1 times 6 over 5 to the n plus 1 divided by n times 6 over 5 to the n. So we simplify this. This is the limit as n goes to infinity and of the absolute value of n plus 1 times 6 over 5 to the n times 6 over 5. This is divided by the n times 6 over 5 to the n. Now the 6 over 5 to the nth power cancels out. Now what do we have left? We have left this, the limit as n goes to infinity. Again, there are no negatives, no oscillation, so you can go ahead and just lose the absolute value sign. That's fine. What we have left is 6 times n plus 1 all over 5n. This is 6 times that n plus 1. 5 goes downstairs with this n here. Now, this limit is 6 over 5. It's greater than 1. So that means, based on the ratio test, that this series diverges. The ratio test says that the limit has to be less than 1 for convergence. If greater than 1 or infinity, then we get divergence. What about this one? So the limit as n goes to infinity of the absolute value of n plus 1 to the third all over 3n plus 1. And now this is divided by n to the third over 3 to the n. This is the limit as n goes to infinity of the absolute value of n plus 1 to the third times 3 to the n, and that's divided by 3 to the n times 3 times n to the third. Now the 3 to the n's cancel out. So we have the limit as n goes to infinity. What we have here is n plus 1 to the third all over 3n to the third. Its limit is 1 over 3. It's less than 1. Bingo. So that gives us here that this series converges. By the ratio test. One more, then we look at the root test. So we have the limit as n goes infinity of the absolute value. Remember that this is the n plus 1 sequence divided by the nth term sequence. This is the limit as n goes to infinity of 5n plus 1 over 2 to the n plus 1 plus 1. That's divided by 5n over 2n plus 1. I think I've written that right. Okay. So we simplify this. This is the limit as n goes to infinity. All the terms are positive, so we'll lose the absolute value. So we have here 5 times 5 to the n times this denominator, and this is 2 to the n plus 1, and that's all over 5 to the n times this 5 to the n times parentheses 2 to the n plus 1 plus 1. So just a matter of simplifying this. Notice that the 5 to the n's cancel. So it leaves us with the limit as n goes to infinity of 5 times 2 to the n plus 1 all over, this is 2 to the n times 2 plus 1. And now we examine this to determine the limit. And to get this limit, we look at the biggest term, if you will. So this is the limit as n goes to infinity of 5 times 2 to the n plus 5 all over 2 times 2 to the n plus 1. Now, the biggest term would be the 2 to the n here and the 2 to the n there. The same term, the same base, same exponent. So the limit, this is the biggest term in the numerator. This is the biggest term in our denominator. So the limit comes out to be 5 over 2. It's greater than 1. And so if that be the case, by the ratio test, this is divergent. This series is divergent. Are you asking how did I get directly and so readily 5 over 2? Well, here's the long way. when you have a limit like this and it's a ratio, take the biggest term and divide each term by the biggest term. Okay. So this term here goes to 0. This goes to 0. This term here, those guys cancel out. So this goes to 5, right? And this guy here goes to 2. So we have 5 divided by 2. 5 plus 0 divided by 2 plus 0. That's 5 over 2. Thank you.